So first of all, I'd like to say hi and welcome all of you for the webinar we are hosting today on aerospace engineering. I'm Ajni Rinuvardhana, the co-founder and CEO of Hybrid Education. We're a company that is passionate about sharing knowledge, raising awareness, and helping students find or identify what truly calls to them or what they're passionate about. Over the past few years, we have worked jointly in organizing aerospace events where we have held a school competition for students to assemble model RC planes, and another event where they had a chance to fly those models. And then we've also done a couple of online quizzes from time to time and some webinars over the past few years. And by doing so, I've gotten the opportunity and the privilege to meet a few students around the country who has great passion and care and genuine enthusiasm for this particular field. So it's been my pleasure to see what we can arrange for the students who may not normally get a chance to get an insight into the field, or it could be that they have other necessarily, even if you're not following the aerospace field, maybe due to that you have other interests or even some restrictions in terms of financials or familial obligations. So in this webinar, what we are trying to touch base on is what aerospace engineering is, what it means to be a design engineer, what are the components and tools that are used specifically in this field, and the soft skills that are used and would be useful for you to have in handy if you are interested in this particular area anyway. Keeping this in mind, let me introduce and warmly welcome Damitha.
Hi, Ajni. Thanks for having me.
Let me give a small introduction on Damitha. Currently, he's the lead engineer at Aircraft Seating, based in UK. His main areas of expertise are design and structural engineering and project management. He's worked across the globe from UK to Sri Lanka to Lithuania. And some companies he's worked at in Sri Lanka and in UK based are KNSI and TAS EU, which where he did structural and design engineering. And then in Lithuania, he worked at JNC, which is also a design engineering company. And he's now back in London, where he's working for Acro Aircraft Seating Company, where he gets to do managing team as well as the design engineering lead role. And I've known Damitha for a very long time now. We studied together in university. He's one of the smartest people I know. He's quick on his feet. His retention and grasping capabilities are on another level. He excels, or I'd rather say thrives, on problem solving. So ironically, he's probably doing roads work in the current role he's doing because I think he's just very, very suited for this. And from what I've heard, it's a lot of mitigating of problems that seat manufacturing companies have to go through. So he's also extremely understanding and empathetic, which allows him to deal well with people and to clearly communicate with his peers, which is a skill on its own. But this in turn, I'm sure helps tremendously in him managing a team. So Damitha, I'm super grateful to start this off with you today. We can slowly dive in. So I would just like to start off with, how did you get into the field?
First of all, thank you for the kind words. Too kind. Yeah. So as to how I got onto the field, well, growing up, I always had a passion for aircraft and also space. Basically, watching all those sci-fi movies and TV shows back in the day, and like people watching, like seeing people travel across galaxies to discover new things in these amazing, how can I say, machines that people have built and thought and designed. So sort of got me into the field, and it was a fascinating thing because a solid metal object flying is not a natural thing. So it could be considered as something like a force of nature, that we are going against nature and everything to make it happen. So it's a very powerful thought, think like that. So it sort of got me into the field. And to tell you a bit about how I got to my position now. So as you told me, we did our bachelor's together in the UK. And afterwards, along with while I was doing the bachelor's, I think you did the same. We both did internships in companies, so sort of that gave me an opportunity to understand what design engineering is, and got me to think, like, because I worked at Sri Lankan Airlines as well as an intern, and I worked at a design organization as an intern. So that gave me the two perspectives of design engineering and sort of aviation in general. That sort of gives the full picture of aviation. So I wanted to do the design side because it was it was something I was passionate about. And then while after my internship, it sort of like gave me a little boost when I finished my studies, that I had experience once when I completed my degree, to find a good job, where I started at KNSI, worked in the UK office and the Sri Lankan office both. Again, as a design engineer. So this is a company that's called the 21J organization. DOA is another word, which stands for Design Organization Approval. So it's, how can I put it? So it's like a company that's given authority on behalf of a big body. So in this case, the EASA. EASA stands for European Aviation Safety Authority. So they have given this authorization to little companies, because to overlook on their behalf and carry out design changes with correct regulatory requirements. So I worked in one of those companies at KNSI, and then I got the opportunity to work for JNC, which was in Lithuania. And then we had the infamous pandemic for a couple of years, which brought down the whole industry, which was difficult for most engineers and pilots and most of my friends who were in the aviation industry. But as one do, you need to find a way to bounce back. And luckily, like, I found this position in Acro as a lead engineer, and which I've been working since last year. So yeah.
Okay, I think I would just from that, since you anyway mentioned that a lot of your experience started off with the design engineering, let me just prompt you for, like, maybe we can talk a little bit on design engineering, like can you see the screen?
Yeah, I can see the screen.
So what does it mean to be a design engineer, in your words?
Good question. Well, from my experience, this is my definition of a design engineer. Is Sorry, can you go back to full screen, actually? I think you did again. Sorry, yeah. So a design engineer, in my own interpretation and from my experience, is a person who designs, well, yeah, it's in the name, designs something that is required for a purpose within given parameters. So design engineering necessarily doesn't have to be aerospace, doesn't have to be mechanical or electrical, or it's a vast, broad definition of a character or person. So in my field, in aerospace at least, again, design engineering is working to find a solution to a problem or something that you can create out of your mind, or a customer requirement within given parameters. And these parameters are mainly governed by the regulations and certification requirements in the field. So when I say certification and regulation, it's simple terms, rules. So aviation is one of the most highly regulated industries in the world, and they're very strict. These are not mere guidelines that will help you, but you can't overstep any of them, because the thing is, you have to always keep in mind the design you do will be tested to a very high degree than most of other things, because this would be fitted or would be used on an aircraft that would be flying 30,000 feet up high with different pressure levels and unpredictable weathers and all these things. So these regulations and rules are the ones that keep us in line to make sure that the design we do meet these requirements, and we build a safe product. So, and also you have to think about because you would be working for a company at the end of the day, and you have to think about the company goals as well to help them meet their revenues and to help them. If it's a new product they're doing, you need to make sure that you can sell the product. It's a marketable product. So all these factors come into play. So again, it's a very broad definition of a design engineer, but again, this slide shows like there are, at least in aerospace, you have two aspects to design engineering. So you have design engineering as an engineer who creates and designs new aircraft and components. And then you have the other engineering aspect of it, where you are a design engineer helping maintain an existing product. Yes, you need help maintaining existing aircraft product, because let's touch the second part first, because that's where the most experience. So the previous slide, I would say. And still not on full screen for some reason, Najee. Sorry.
Just a second.
Yeah, there you go.
Is it?
Yeah, better. So yeah, so this is basically aircraft aftercare, which is the bigger industry in aviation engineering. The designing part of an original equipment or original aircraft is a very limited industry, but the aftercare side is a much more thriving and a much more viable industry, if I would say. So in this, the main things you would get to do is help with aircraft modifications and repairs. So as I said, if this is also again governed by regulations, because even though if it's not a brand new design, you still need to make sure that the modifications and repairs you do on the aircraft keep the aircraft airworthy. So airworthy is the technical term to say it's fit for flight when this is done. So especially with passenger aircraft, when people are involved, not just personal aircraft. So especially when it's passenger aircraft, commercial aircraft, these regulations are very tough, and there are very strict guidelines that you have to navigate through. And for that, you would need the soft skills that we would probably discuss in a later slide. So this would mean the technical competencies and the software skills you need, the softwares you should be familiar with if you want to further yourself in these industries. Ultimately, these designs and repairs lead into aircraft maintenance, which is the main purpose of it. So to prolong the life of a product, because aircraft are very expensive and just not one-time use equipment. So you try to use it as long as possible, and they move from owner to owner, just like a car you would buy secondhand. So aircraft are sold secondhand as well. So normally, like big airlines buy the brand new aircraft, like flag carriers. These are the sort of like the main airline in the country. Those big flag carriers buy brand new, and after a certain time of using, they would transfer them in the second-hand market to other customers that would buy them and still fly them for good 20, 30 years. So as design engineers in this field, your sole purpose is to help them preserve this equipment and help them run it as required. And then we have the other design aspect of it, the design engineering of brand new equipment, components, and aircraft, which is what I'm working on now. So I'm not designing whole aircraft, but I'm designing aircraft components. So this is mainly, again, as the previous design engineering aspect, this one is also governed by regulation. These are the guidelines that help you create a whole new design, but within the required parameter. I understand it's a very annoying thing to have, that if you're a very creative person and you have like brilliant ideas about how you do things, when you come to aviation, you can have these things, but you still need to know how to thread the needle between these regulations and everything. So it's a skill you learn with time. So and you learn to polish your skills about designing and everything with time, because the more you do these things, the more you understand the more your brain gets calibrated into what can be done and can't be done, and your thoughts and everything gets adjusted accordingly, and it's again built up through experience. Yeah, we have again soft skills and softwares that are needed. So soft skills would, again, technical skills you need to design. So that would mean basic understanding of not basic, a bit of in-depth understanding of physics, a bit of chemistry, because you need to understand materials, and then electrical integration is required. Then you need to understand a bit about that. But mostly you have dedicated avionics and electrical engineers when you do a design. And then all of this lead into manufacturing and manufacturing of aircraft and components. So that means the designs you do should be, you need to understand that when you create a design, let's say a simple thing that you make with sheet metal, you need to understand whether they are able to form this sheet metal into that shape with the bend radiuses you do. So it's like if you bend a sheet, there's that edge, there's a thing called a bend radius. So this is defined by the material strength, the thickness of the material. So there are certain thicknesses that can't be bent at 90 degrees, so you can't achieve that radius. So you need to be mindful about these things when you create a design, whether it could be manufactured, and when you do the manufacturing, does it require like very special machines to achieve that requirement? So always need to be able to find a balance between innovative designing, creative designing, and along with the achievability of it. Because mostly, if you are in this designing side of things, you'll be looking at mass manufacturing. So it needs to be cost effective and viable throughout the life cycle of this product. Yeah, so yeah, I've been going on. So that's a bit about design engineering, I would say. The two aspects I see in design engineering, rather.
So we can actually maybe talk a little bit on the repairs and modifications in aircraft, as well as like how you normally go on to classify the primary and secondary aircraft structures, and just give maybe like an insight.
Sure. So as I told a bit earlier, the design engineering as element of already existing product and aircraft. So for an aircraft, let's say the aircraft comes with a bunch of books and documents. So it's like buying a car and you get a manual. And I know nobody reads the manual in a car, but in aviation you have to read the manual. Otherwise, you can't do many things without reading it. So among these manuals, you have the AMM, which is the aircraft maintenance manual, which is like the sort of like the main document used in aviation. So this would tell you how to maintain and do routine maintenance practices. When I say maintenance, it means how to remove something from somewhere and how to install it back again, how to clean it. If you have to put lubricants in something, how to do that, and what's the type of material that needs to be used. So all these things are categorically written and documented in this document. If you don't mind, I would like to share an extract from an AMM. Okay, bear with me. Shall I take control of the screen? Share. Okay. Okay. So this is an extract from a Boeing maintenance manual. This is a 737-300, 400, 500 variant. Variant maintenance manual. So this is what you call 737 Classic. 737 is the most common commercial aircraft currently used. So, and Classics were very old versions of it. So they started back in 70s, even 60s, if I'm not mistaken. There were earlier variants like hundreds and 200s came in 60s, if I'm not mistaken. So in these manuals, it tells you. So this is like the first chapter where it describes the aircraft, the main parameters. So if I can quickly show you. So this station is how you identify a position in an aircraft. So stations, or called body stations. So let's take like a Cartesian plane, which is a XY axis plane. So you define a point by giving the XY coordinates. It is exactly what we are doing on an aircraft. So the X coordinate is defined by the BS value, the body station, and the Y coordinate is defined by the BL value, the body line. So body waterline. Sorry, not this one. This is the Z coordinate. So that's the with me, it should be. Sorry, it should be a different document. So as I told, like it's defined by two coordinates, and it can pinpoint to a position on an aircraft, and which sort of lets them know where it is that you are doing the repair or modification. This is how you instruct someone to get into that place and do the design change or repair or modification. And then along with that, you have, this is another chapter of the same document. This is for the cabin interior, which is chapter 25. If you work as a design engineer, this is one of the most common chapters you will have to go into. So in here, it will show you all the installation procedures and repair procedures, not repair, maintenance procedures rather. So for example, if you take this step, it says inner window and shade removal. So it tells you how to remove it, and it goes step by step, and it tells you which tools to use, which views that you can use to identify these things, and so basically telling you each and every single thing you can do. So this is the AMM, and then if we go into, this is the SRM, which is the structural repair manual. So this is the second most important document used in aviation. So this is where it shows, this is again the first chapter of that. It shows what you can do and can't do in an aircraft when there's a damage. So if you can see this, so the areas hatched here are considered aerodynamically critical areas. So whatever repairs do on the skin or anywhere within these shaded regions, you have to make sure that required aerodynamic smoothness is achieved. So which is called the drag coefficient. So you need to understand how to reduce drag coefficient in your designs, including smoothness and among other things. And what else? So again, like this is I'm just trying to show you a little bit about what these documents are. I'm going to show you something interesting I had found before. Give me a second. Oh yeah, this one. So see, this is a full breakdown of those body stations, and body stations and wet lines. Those are the coordinates. Sorry, my mistake. So if you take a cross section of an aircraft, it looks like this, and each cross section from each frame, so these are called frames, are different because the profile of the aircraft constantly change to account for different requirements. So this is another quick image of an aircraft, and this shows the pressurized and non-pressurized regions. I think we will touch this later on. Ajini, what do you think about pressurization of aircraft?
Yeah.
Yeah. Okay. I will keep the screen back to you. Sorry. So those are some of the documents that you work with. These are what you call the manuals that you work with in an aircraft. So where do we come in as design engineers? If all the things that are needed to be done on an aircraft is documented, why do you need engineers if it's already defined? Well, the thing is, everything and anything that can happen to an aircraft is not documented. So there are instances where it's, so let's say they want to, let's take the repair side of things. So modification, I'll come back in a bit. Let's say there's a damage on the leading edge of the wing. Leading edge is the front surface of the wing, so which is which is part of the whole wing design, and it's different parts, and it's assembled together. So there's a damage in the leading edge of the wing, and in the SRM, the structural repair manual, it's defined how to do a certain repair for this damage, but it has a limitation. So let's say like the damage could be 3 inches wide and 1 inch thick. So that's the maximum it can go according to the document. So if the damage is higher than, it's bigger than that. So 2 options for the airline. One, they can go back to, in case of Boeing, go back to Boeing and ask for a replacement part or a way to repair this, which is the best way to do it, but it comes at a cost, and it comes with a big like a time requirement, because Boeing, as you know, it's not catering to one customer; it caters to the whole world. So them trying to mitigate your problem and getting to handle your problem is it comes very low in the priorities, and you will eventually get an answer from them, but it'll take a very long time. So that's where design engineers like us come into play. So we, again, as I told you, we have been given the authority by governing bodies who make these regulations to do these things on their behalf and on behalf of Boeing. So we have the authority. So what we do is we find the best way to repair this problem and try to do justification for these repairs. So that is the other element of design engineering, justification of your design. So this justification could come as so it could be a structural justification. So that's so you justify your design as it's structurally sound. It can withstand the loads, and it'll meet the requirements of the aerodynamical requirements and all these things. And at the same time, you have to do certification requirements. So this is making sure that you have used correct materials in the design, that you have followed the correct procedures in the design. So these are the things that you sort of have to keep in mind when you do this is repair incidents. And then you have the modification of it aspect of design engineering. So the modification is mostly, again, most of the things that need to be done on an aircraft is documented, but there are instances where airlines have to do changes, mostly for the cabin, and then outside as well, but very less, but mostly for the cabin. So I've told you, like, aircraft move from one owner to another owner. So when this change happens, so the aircraft need to, how can I say, it needs to get the what's the correct word for it? It needs to reflect the company. So that means, like, it needs to have the colors that the company use, the environment the company use, and so it needs to get customized. So it's more like a customization. So this is where again we step in. So the correct way to do this would be to go to Boeing and to say, okay, we need to remove what's inside completely and install a whole set of new things with these colors, and it should look like this. And these are the lights need to have, these are the seats that needs to go in. We need to have business class, we need to have economy class. So these are the configurations and, like, new requirements for the new owner of the aircraft, so the airline. So it needs to meet the airline requirements. So again, as I told you, you can go to Boeing or Airbus depending on the aircraft, but you face the problem, as I told before, that you will have to wait a very long time and have to pay a very high premium to get these things done. This is where design engineers come in again. So we do the design. Of this new configuration. Again, I think it would be better if I share. What do you think?
Yeah.
Okay.
You can just go for it. Yes.
Let me share you something. Again, I'm not at liberty to share everything, but I will show you these things. So this is called layout of passenger accommodation, or a LOPA. In this case, we are doing 88 BC and 24 YC plus 126 YC configuration. So That means BC means business class. YC is a very it's an old term used. So what it stands for is Yankee class. So it's an old terminology from the US when they started aviation. So Yankee class is considered economy class, or you can call it EC as well. So this is the business class section, and you have the economy class section. So again, a customer would come to you, your company, and ask, how can we reconfigure an aircraft to fit my requirements? So this is what we do. We take the seats and we install them, and then again, along with these installations, you have to meet certain regulatory requirements. If you read right here, so we have to tell what this is the justification we do for these installations. So we do the installation according to the frame spec. So frame spec is a document that's issued by the OEM or the TC holder. TC holder stands for oh God, I can't remember. Type certificate holder, sorry. So type certificate is sort of like it's like a birth certificate for an aircraft. So it's the owner of that birth certificate is the manufacturer, basically. So in this scenario, this is a Airbus. So this tells you what you can do and can't do with their aircraft. So this is mainly for modification purposes, and this is an emergency exit. It tells you what are the distances that needs to be maintained in case of an emergency evacuation. Does it have enough room for passengers to get through? And then you have the other requirements, which is this head injury criteria. These bulkhead clearances are governed by this arc we define, which is called the head strike arc. So in an emergency condition, when you're lunged forward, you need to make sure that the passengers don't withstand high degrees of damage and injuries. So this is something you have to be conscious about. And along with that, you have this is something, again, quickly, these are the PSUs. PSUs stand for passenger service units. So these are the oxygen masks, the overhead lights, and everything that when you fly, you have these lights ahead of you. And so along with these lights, the most critical thing is you have oxygen masks. So you've probably seen the presentation normally this flight crew gives before flying, saying where the emergency exit doors are, how to put on a mask, how to put the life vest on. So this is where you get the mask from. This is a whole unit. So, and again, it's governed by regulation where it falls when the seats are rearranged. So let's say you are rearranging the seats, you need to make sure that you arrange these PSUs as well. So again, not everything as a design engineer, but I'm just trying to show you a bit.
Good question, Damitha.
Haven't I been sharing the screen?
Not this.
Okay, I'm really sorry. So I thought I was sharing the screen. 1 second. Oh, sorry. So my bad. So this is, as I told you, the LOPA, which is you can see the screen now, right?
Yeah.
Which had the configuration of 158 packs, 8 BC, 24 plus 126 YC, Yankee class. I told you these are the business class sections, and these are the economic class sections. And if you can see, like everything should be dimensioned correctly, and there's an aerospace standard for doing everything. So you need to make sure when you do these kind of drawings that you meet all the requirements. And these are the sort of emergency exit regulations I touched you about. So this is the frame spec I was talking about. There you go. So, and then you have aisle width requirements. All these things are sort of defined based on an emergency situation, an emergency condition. So the design of an aircraft is, all the components and everything it's mainly revolving around the fact that you need to keep the passengers safe. As I told you, what we are doing is not natural. It's a metal object flying, so things can go wrong, but it doesn't most of the time, touch wood. But But we are trying our best to have not just one safety measure, but 2, 3 safety measures layered on top of each other to make sure it doesn't happen. So and this is the passenger service unit layout I was talking about. So this is the zone that the mask should fall. So when you do a seating change like this, so you need to make sure that all passengers have access to these oxygen masks in case of an emergency. And then you have this is the electrical side of things that I told you that you need to have a little bit of idea. So you need to make sure you need to plug in the correct connectors everywhere, because yeah, it's not just a
Quick
mechanical.
question. Yeah, just wanted to touch base on like one of the things I think you mentioned before to me, so for example, when taking into consideration the safety and the sort of like the force of impact to reduce the pressure around the seating and even the seat in the front of us when we're seated. Can you maybe touch a bit on the designing of it to like maybe the material or even how you kind of contain the pressure?
Okay, sure. Okay, let's go with an okay. So this regulation is called dynamic test required, the dynamic landing condition, sorry, which is defined on this document called a CS. CS stands for Certification Specification, which is written by FAA, which is the Federal Aviation Authority, and EASA, the one I mentioned before. So these bodies, they get together and define these parameters. So these are the rules we have. So in this situation, the latest regulation, so back in the day, a seat and a passenger, when they're seated, should be able to withstand 9G acceleration load. So that's G stand for gravity. So we are at 1G right now. So 9G is like, it's a lot. So it's a very big amount, but it was tested statically. So that means you fit an aircraft, you fit a seat in a rig, you put a passenger on and you pull at 9G and see if it breaks or if things come apart or things like that. But now they have identified it's not enough. So they have moved on to a different testing criteria called 16G. So it's not even 9G now. We test the seats and everything in the aircraft for 16G. So that's withstanding a deceleration. So it's not acceleration, it's deceleration of 16G. So the seat is made in a way that the passenger is safe, is a very broad term, but trying to keep the passenger safe at 16G. So, well, let's say, oh, good example. So you're in a car, you're not the driver, you're a passenger, and the driver has to brake very abruptly and quickly. So what happens? You lunge forward. So this is where from your torso you move forward, and in doing so, there's a chance of your head hitting the seat in front of you, because if you have gone on seats, economy seats aren't very wide apart, so they are very close to each other. So your head, there's a chance that it'll go and hit you hit your head in the seat in front. So when doing the design of these seats, you have to keep that in mind, that in an instance like this, that the passenger have minimum head damage. So it's called head injury criteria. It's a requirement we have to meet. So most seats, the new ones at least, the old ones didn't have this requirement, but new ones have to make sure that it meets this head injury criteria. And then it has to do testing for femur loads. So femur bone is the one in your thigh. So in case of an accident, your knee goes and hits the seat in front. We need to make sure that these forces won't break these femur bones. So again, you have requirements for that. So yeah, these safety aspects are built into the seat. It's one of the it is the primary component in the aircraft, apart from the structure and everything that keeps you within the cylinder. But inside the cabin, the seat is what keeps you safe in case of a accident. Well,
and the seatbelt.
A reasonable accident that you would.
And the seatbelt.
Yeah, and the seatbelt. Yeah, seatbelt is part of the seat. Oh, let me show you. had something. I want to show you a seat design. So this is a seat we've been manufacturing at my company. So as you see, like all these designs are done with a 3D engineering software, the CAD softwares called CATIA in this instance, and you have SolidWorks and other things that used in the industry. So, and then you get a 2D representation as a drawing. So this is a seat where you get, probably you haven't seen these things in an aircraft, but you have the seat belt, sorry, the life vest right under here. That's when the cabin attendant normally says your life vest is stored under the seat. So this is where it is. So you get the life vest here, and then you get the seat belts, and you have the armrests and the seat backs. So as I told, this armrest, sorry, the seat belt is what keeps you in the seat in case of an emergency. This is again regulated, and this is, so when you're testing the seat, you put a big dummy in here and do the testing and make sure the seat belt doesn't come off and it doesn't have like pressure points in the belt that harms the passenger. And then you have, is this the one? So as I told you, the seats are made in a way that in case of an accident, the seat back needs to make sure that it doesn't create the head. It meets the head injury criteria requirement. So at least in our product, what it does is it breaks the seat forward. So there's a switch, a mechanical, not a switch. It's like a fuse. It's called literally called the Hick fuse. Hick stands for head injury criteria fuse that breaks at a certain force, and it absorbs the force before, and then it breaks afterwards. And so doing so, you won't get the reaction force back into your head more than the allocated. So that's a safety mechanism built into this. So that's the regulation. Well, regulation is, honestly speaking, it's a big topic that it's a boring big topic that we can go into at one time if you like. But
yes, maybe in the future. Yeah, it's a broad topic to cover.
Yeah.
But I'll just ask on the structures and like one last question of like, I think this is something I received from one of the someone of you who signed up. That is, how do aerospace structures differ from other structures, and why is lightweight so important in the design?
Yeah, good question. Okay. I'll talk about the lightweight one first, because yeah. So how aircraft fly is overcoming forces. I think we've had a little slide like that before. Can you remember? We made for another presentation. Do you have that? No. So okay. So basically, you have lift, which is acting up, and you have weight of the aircraft, which is so let's take this then aircraft. You have lift going up. You have weight.
Just a second.
I think you had that.
I do.
Yeah. Okay. Till she shares, and then you have the thrust, so which is the force that makes the aircraft go forward, and then you have drag, which is the aerodynamic force that slows the aircraft down. So thrust is the only force we artificially generate, and everything else sort of appears. Weight is always there, and then the lift is a reaction due to thrust, and the wing profile and the wings and the other aerodynamic components. And then you have drag, which is basically surface friction and other turbulent forces that act on the aircraft. So the aircraft is designed to reduce drag and to reduce weight. So these are the reducing drag is, again, it comes to aerodynamic smoothness and other things. So by reducing, if you increase the weight of an aircraft, the force required to fly becomes greater and greater because it needs to overcome that initial load. So every design you try to do, you try to reduce the weight of the aircraft. So a reason, so this is a reason, there you go. Lift, weight, thrust and drag. So the one, the only element we can, so the, the most easiest element to control in this calculation is weight. So when you do the design, if you can keep the weight down, you are likely to have less wastage of the propulsion energy you're creating. Because I think that's pretty much it. So to do so, what you do is you find materials and designs to reduce weight. For example, uh, most of the aircraft structures are made from aluminium, and like very modern aircraft like A350s and 787 mostly, they have moved to like a 70-80% composite design. So composite is it could be carbon fiber composite, it could be fiberglass composite. So it's the composite is where you have a matrix where you have the resin layers and fiber layers working together to create the required structure. It's done through the orientation of these layers. So to for the requirements. So if it's a linear load, it's made in a different way. If it's a shear load we are trying to overcome, it's made in a different way. So these factors you factor in and do the simulations through finite element analysis or structure dynamics or any other software that you do the initial testing, and you try to create a design as light as possible, but keeping in mind that it shouldn't break the company trying to make that. So it needs to be cost effective as well. So the best solution would be to go into very fancy materials, like you can go for magnesium, which is even lighter but expensive. So aluminum is sort of the god tier for aviation. We use titanium as well, but very less for bolts and other little components. But generally, design wise, you use aluminum because it's very light, and there are different types of aluminum alloys throughout the spectrum with different stiffnesses and different material properties, yield strengths, tensile strengths, and so you have something that matches your requirements. You have things as soft as how can I say? What's as soft aluminum? A very soft aluminum. I can't come up with an analogy. And then you have very strong ones like harder than steel, and it can withstand any load you throw at it. So this is why you try to keep it light, and this is how you keep it light. And then the first part of the question, how it differs from other structures. Well, it's the basic theories don't change. It's pretty much it. But as you said, lightness come into play. And
Sure.
yeah, and
And
the
the environment.
biggest difference is the loads it withstand, the environmental conditions it goes through. So an aircraft is, if I share my screen again, this would be a good one to show. I had, talking about lightness, if you can see, all these legs are made from aluminium. And can you see these holes in here? So these are lightning holes. As it says, the whole purpose of this is we have taken off material from areas that we think the load path doesn't support from. So this is an I-beam. You'll get to learn about these things maybe now or later. So in an I-beam, the material in the middle doesn't matter too much. So what we do is we take off the material in the middle to reduce weight. So it's, yeah, as I told, weight saving is sort of the most important one. Okay, pressurized and unpressurized. As I told you, I'll come back to this one. So when you fly, okay, go to this. Can you see my screen full still?
Yeah.
Okay. So when you are when an aircraft goes above a certain level of altitude, the pressure drops in the environment. So the maximum we can sort of manage as humans is around, not the minimum, the maximum is around, not maximum, but a comfortable level is around 10,000 feet. When you go beyond 10,000 feet, the aircraft needs to be pressurized. So in the industry, there are pressurized aircraft and unpressurized aircraft. So unpressurized are these small little Cessnas and all these ones, that single engine turboprop ones that you have seen. People can fly and land without too much of a hassle, and it's easy to maintain because it doesn't have that pressure difference problem. But the pressurized aircraft, mostly these long haul passenger ones and almost all the commercial aircraft, needs to be sort of maintained. A pressure needs to be maintained within the cabin so that people don't suffocate. So when the higher up you go, the thinner air becomes, and it becomes more difficult to breathe, and because there's less air, less particles, and the pressure decreases. So it's a, can't remember the name of the principle, but yeah, it's less material, less the same volume and less material, so less pressure. So to withstand that, so what the aircraft does is it pressurizes itself. So at ground level, it's not pressurized because we are okay. But when you start climbing, this aircraft starts pressurizing itself. So that's when you normally feel your ears getting locked up, and you feel the difference. Like you can, it's a physical difference as well that you can observe. So when it's flying at 30,000 feet, the aircraft is pressurized at 10,000 altitude pressure. It's not pressurized to the ground level pressure. It's pressurized at 10,000 pressure. The reason being, it's like a container, a tin container that's pressurized, and outside pressure is low. So what it's trying to do is push the walls out all the time and try to expand, because the inside pressure is greater than the outside pressure. So the whole purpose of this aircraft structure is to keep that thing in one place without blowing up. So it gets pressurized and it flies, and it lands, it depressurizes again. So this is called a pressure cycle. So pressurization, depressurization. And also the aircraft goes through the constant vibration from the engines and from the wind. So it has these micro flutters on the wings and everything, and it carries throughout the structure. And then you get the vibrations from the engine itself, and it resonates throughout the structure. So when designing an aircraft, structure-wise, structural repairs or new designs or whatever, you have to make sure that these loads could be how can I say, the structure should be able to withstand all these loads, and not just once, multiple times, over and over again. The aircraft, the whole life cycle of the aircraft, these primary structures shouldn't fail. So it's primary structures. So we had a slide for that, right? What are primary structures, secondary structures? Yeah, can you please share that? Sorry.
Yeah. Just a second.
So yeah, so when you do structural design, so the two things you need to keep in mind.
Can you see?
Yeah, we can see. So in an aircraft, it's defined as you have primary structures and you have secondary structures. So the secondary structures are the ones that are hatched. So not a lot. So the primary structures are the majority, at least on the outside of the aircraft. So all these primary structures needs to be able to withstand cyclic pressure loading and the vibrations and maybe a harsh landing. So all these things need to be taken into account when you are doing aircraft structures, which is a very dense subject. For me, at least, I haven't done too many primary structure work. I have only worked on secondary structures, because primary structures, normally outsiders don't get to do it. It's always the aircraft manufacturer who deals with them, because we don't have, because the thing is to understand how we can do a repair or a structural change, we need to understand, we need to have all the information, all the data about these changes and vibrations and pressure cycles and everything that an aircraft goes through. And it's not even just one instance. It needs to account for all the possible scenarios. And this is a bit of information that the manufacturers don't share with us. So without that information, we can't simulate a real life scenario and see if the change we did can actually withstand this loading. So this is why structural repairs is a very uh, it's
Like,
very limited to what an outsider can do to an aircraft than to what
yeah.
the actual manufacturer can do. So I think I sort of answered the question, I hope.
Yeah. Yeah, I mean, I think maybe just look at also like move into the soft skills a little bit so that,
Yeah.
yeah.
Soft skills. So if you go to that slide, I can talk about the softwares that's been used. Yeah.
Can you see?
So yeah. So basically, which sort of engineering you do could be, I'm talking about design engineering. So it could be, as I told you in the beginning, it could be sort of like the initial design of aircraft to manufacturing and all that, or aftercare side of things, so the modifications and repairs. There's a set of skills, technical skills that you need to have in your arsenal if you want to sort of look into jobs in these fields. Uh, 3D design software, so basically CAD software, it's sort of like the bread and butter of engineering. So you need to be able to create something that you can visually you can visualize. Sorry, you can imagine. You need to be able to visualize it. So you need to be able to create it in real, sort of like in a 3D software before you go into prototyping and creating a model of it. So this is where you should be able to translate your thoughts and ideas into an actual sort of visual representation of it. So for that, the main softwares used are, as you can see, we have CATIA, which is used mostly related to manufacturing aspect of things, because it's easy to translate CATIA information into uh, CATIA information into manufacturing a CNC machine or something like it's easy to translate that, and it can be sort of integrated into uh, life cycle management software. This is how you sort of digitally manufacture something and see how it manufacturing goes and everything, and you build a seat or a component or an aircraft from scratch, and then you do the whole manufacturing process digitally to before you implement it in how can I say, an actual world scenario. So you have CATIA, you have SolidWorks, and of course you have trusty AutoCAD, which are most used for 2D drawings. And then you have the simulation softwares on the other hand. You have SimSolid, ANSYS, Nastran is a NASA developed software that's very specific for aerospace, but the other ones are sort of generally used throughout the engineering industry. Uh, and then for fluid dynamics, you have what's it? I think ANSYS has a good fluid dynamic flow simulation software, and so does SolidWorks, which honestly I haven't done much of it. But you need to have like if you have a working understanding of them, any of them, it's good. So if you're looking into something, it's better to at least have checked the software first, gone through it a bit, played around with a bit, so you know where the tools are. Because most of the skills, these things you can learn in university, but every company has their template, has their way of doing things. So you have to learn the new system. So it's something that I have done. I know how to use these softwares, but each company that I have worked for have its own method of doing things, different different routines they follow, different templates they follow. So according to that, you need to adjust your skills, but the fundamentals still remain. And I think you have missed another one, which is called Smart Team, another software that's good to be aware of. It is it is sort of like the management software of all these solid sorry 3D work you do. So it's like Windows Explorer for 3D stuff basically.
And
Uh,
also, I think just want to mentioned that most of these softwares that, though it's specifically we are currently talking about aerospace, but if you're interested in learning and even while in school or in university, it's still interchangeable across so many different engineering fields. Because if you have the skill to learn like and design and do the drawings, I think it would anyway be kind of beneficial for you to get an understanding. Or because I think we get a lot of these questions that I've received so far has been if the students have done either they are currently studying mechanical engineering or electrical, whether they can kind of switch into aerospace or whether they have a chance of working in the field. So I would just like to have your thoughts on it.
Yeah, I think definitely. So aerospace engineering is just a big definition of a multitude of engineering disciplines. So within that, you have the mechanical engineers, which are the people who design these structures and the other moving components and all these things. And then you need the electrical engineers, who are mainly called avionics engineers. So these are the people who do the integration of electrical systems into the aircraft, because maybe 100 years ago an aircraft was a very mechanical system, but not anymore. It's mostly aircraft systems that keep the aircraft afloat and safe. So avionics or electrical is very critical. And then you have the aerodynamic side of things, which again you need. It's a very aerospace forward aspect, but you have aerodynamics in motor vehicle design. So if you take Formula One or any other modern car these days, especially electric cars, aerodynamics is sort of like the key. They try to reduce the drag all the time, the drag coefficient. So this, as I told you, it's the force acting against the direction of motion. So these things are very transferable skills. So even if you have studied mechanical, if you've studied electrical, if you've studied computer science, uh, computer software programming, and all these things, they are all part of aerospace design, aerospace aeronautical design. So of course, there's if you're worried about that, I would say you shouldn't. If you have a passion for aerospace, you have a way in. All these skills are transferable.
Yeah, thank you for that. And I think if we were to go, can you see my screen?
Yeah.
Okay. And I think from the soft skills, in terms of if you're actually working in terms of the paperwork and actually putting all these things in order, what you do from the design, and then sort of, I think it's kind of like putting the practical into communicative. Yeah.
Yeah.
What should they mind?
So language skills, yeah, you need to be good with your English, because aviation doesn't matter where you are. It's done with English. English is the global language for aerospace. They have made it in a way because, like, you could be having pilots who start from China and a flight journey from China and land in, let's say, India. Okay, so you need to have a common language in the middle to make sure that the communication is done correctly. So that's English, and it's the same with the engineering aspect of it as well. So all the technical documents, all the regulatory documents, everything and anything you can think about is written in English. So you need to be proficient in your English. Again, as an engineer, the English you use is not the same English you and I talk like this. So when you do a engineering document, it's a very sort of like straightforward sort of. You should be very accurate and uncompromising as possible when you give an instruction. You don't sugarcoat things. You don't make it look nice and fluffy, and you don't do any of that. You just blatantly tell what the operator needs to do when they go into an aircraft. So they would, okay, maybe can show you something in that regards. Okay, if I share this, give me a second, because it's better if I can show you. Can you see my screen
Yes.
as a full screen?
Yeah.
Okay. Okay. So if you see, let's take a quick instruction. The first one, refer to Airbus PMS. Blah, blah, blah. PMS stand for process. Okay, I can't remember. I'm sorry. Document and drill this hole, 2 per location, depth to suit, insert. Okay, that means that you need to drill it in a way that it suits this part numbers, this insert. So it needs to be it needs to be drilled in a way that it can accommodate this insert. And on right hand, curved partition, fold face of lavatory. So it's not the normal English you and I read on a book. It's a bit different. This is the engineering English we sort of use in industry. Again, it's not something that you can read off a book and learn. It's something that you pick up when you join the industry. And sorry, yeah.
No, I think there was a question on the chat from Katarshika. Is aerospace engineering and aeronautical engineering are 2 different types?
Yes. So aeronautical is something that it's a design and maintenance and all that about aircraft that flies under the stratosphere, if I'm not mistaken. So stratosphere is different layers of altitude environment. So anything that flies under that is called an aeronautical product. Please don't quote me on this. Maybe I'm wrong, but this is
you're fine.
I have. But beyond that, it becomes aerospace. So again, principles most of the time are similar, but aerospace takes design into a different extreme. So you need to account for a vacuum scenario in space and lack of gravity. So aerospace is basically the degrees we study are more broadly defined as either aeronautical or aerospace. So when you study aerospace engineering, you will get elements of this lack of gravity and lack of air pressure, vacuum scenarios, and the other things, the radiations and all these things. So these are additional information you will learn. But the reality is that an aircraft or any spacecraft needs to fly through our atmosphere to get into aerospace. So it needs to withstand the aeronautical requirements as well. So if when you do aerospace, you learn about aeronautical and a bit about space. And if you do just aeronautical, you learn about what's it to design something and manage something within our atmosphere, or stratosphere rather.
I think we can maybe shift from there to like, so when you said aeronautical, if you look at the field and in terms of even what, let's say you section it out with, you have design engineering aspect of it, then you have the maintenance aspect of it, and then you have the manufacturing that falls on design. But also, so maybe that's some pathways you can look at as an aeronautical engineer, as well as even as an aerospace engineer, then you might have a bit more options in terms of the spacecrafts. So companies like SpaceX or like NASA or some other companies that will mainly look at the jets and anything that's related to spacecraft.
Yeah.
So how maybe you can shed some light on like what are the options they have in terms of career pathways?
Okay. Based on my experience, as a Sri Lankan doing either of them, aerospace or aeronautical, at least for me, when I was looking for jobs back in the day, about 10 years ago, it wasn't the easiest because we didn't have the same access to not access. It wasn't widespread social media like what we have now. LinkedIn was a very primitive level, and even like the communication, like even job boards weren't that active as of now. So it was difficult for to find jobs. But as I told you, when you do aeronautical engineering, you have 2 parts to go: aeronautical, aerospace. Sorry, forgive me. You have 2 parts. You can go into brand new design of things, and then you can look into the maintenance aspect of things. So as I told you, the brand new design of an aircraft it takes about 10-20 years to design a new aircraft. So it's an ongoing process that you join in the middle, and then if you're really lucky, you'll get to join in the middle and then be part of that process. but the biggest market is the maintenance side of things, the places I've worked before. But now I'm working on actual design and manufacturing of components and aircraft, which is the first side of things. And before I was working as a design engineer for maintenance organization, so maintenance of aircraft. So this is where you have the access to all the aircraft that's ever flying right now in the world, and all these things, all these aircraft have to go through some maintenance routine or modification routine at some point. So the market is much bigger for you. When I say market, the career market. So opportunities are much bigger, and this is for purely for design engineering. And then if you do aerospace, then of course you can get attached to big bodies like NASA, and you have the European European Space Agency, ESA, sorry. And then you have the Indian space program, you have the Chinese space program, you have the Russian space program. And so all these space programs are there. And then you have the private space programs like SpaceX. And then there was more, I can't remember from the top of my head, but, and not just like this. So just like the only design company for aircraft is not just Boeing or Airbus. So there are other companies like the company I'm working for that develops components and parts to these aircraft. So just like that, even for spacecraft, there are other companies, affiliated companies that are looking for design engineers and manufacturing engineers to produce these things to go on these spacecraft. So you need to look at this design engineering aspect in a broader way, and try to understand what sort of makes you excited, and find that and target your energy in getting a job in that field, in that space, basically.
And do you see, I think one of the questions we had, like career aspects for women. So do you see any restrictions, or is it simply it's available and like ready or like welcoming to all jobs, pretty much?
Sorry. Yeah. So I have experience in aerospace, and I have experience in a couple of mechanical companies and civil engineering as well, weirdly. But aerospace is, aeronautical. It's just go with this. It's the same definition when I say aerospace or aeronautical. It's one field that I can genuinely say that has no restrictions if you are a man or a woman. So it's only your skill that defines you, where you get to and what you get to do. So like, for example, the other lead engineer I'm working with in my company is a lady, and she is actually going on maternity leave right now, and it bears no effect for her career path, because she can pick up right where she stops when she comes back, and that position stays open. So it's her skill that defines that we don't need anyone to replace her. We need to have her. So I have seen this throughout the industry, and I can hand on my heart, I can say it has no restrictions whether you're a woman or a man. You will have no issue navigating yourself through this industry.
Thank you. And I think we'll move from there maybe to, let me just share the screen again. Can you see the screen?
Yep, can see.
Okay, I think that's the question I wanted to ask you. So from your experience in terms of working in UK and then Lithuania and in Sri Lanka, what are maybe the experience that you have, that you've seen the approaches that different companies take? Any subtle similarities or even differences that you think is a bit more efficient from one place to another?
Yeah, sure. So one good thing about our industry is most of the standards and requirements are global. These regulations don't change from country to country. They are common through. If it's the Sri Lankan civil aviation we're talking about, or UK civil aviation, or the federal aviation, FAA, or the European safety aviation. So doesn't matter where you are. All these areas are controlled by a very common set of guidelines. So whichever the country you work, things you learn about in our industry is transferable. Doesn't matter where you go. And the other good thing is English. It's always done through English. So you are not at a disadvantage if you go to a country that doesn't speak English, because still our industry is run through, yeah, it's broadly communicated and worked on English. So that's the common side of things. But the other aspect is the people element. You need to learn how to how to how to fit to different environments. You have to be adaptable if you're planning on, like me, just going to places where opportunities present. So as I told you, like, since our industry is niche and small, unlike other industries, especially design engineering, when you gain the correct level of experience, you get hunted by headhunters. Basically, they come to you and present you with opportunities. It's not something that's going to happen within 2 or 3 years, but you need to build yourself a good profile, good experiences. So once it starts happening, you don't need to start you don't need to go looking for jobs come looking for you, because you are a very uh, capable person in a niche industry. So when this happens, you get opportunities in different parts of the world, and you need to understand this is more about sort of like how to, not about engineering per se, but like as a person. So
Okay.
you need to be adaptable for situations. You need to know how to navigate different cultures. You will meet people from, like, for example, when I worked in Lithuania, I used to work with multiple, like, people from multiple countries. Like, had German people working with us, French people, and you had Russians, and you have Polish people, Ukrainians. So each person, how they talk to you and how they interact with you is different, and you need to keep in mind that their culture is different as well. For example, a Russian, an engineer talking to you would be, it's a very unsympathetic way they talk. Again, you need to understand there's a big language barrier between
And the
Russian
tone of
and
voice.
sorry.
That could come off even the tone of voice, right? It may come off
Yes,
just
yes,
it's just
tone
a
of
simple
voice.
way.
Yeah,
Yeah.
there's a big language barrier, and the way they speak and way they pronounce certain things, you would think like, oh, that's very forceful. Why is he angry with me? It's not anger. It's how they speak. So you need to understand that. And then you have Germans, on the other hand. They are as direct as it comes. So they will tell you, you are not doing a good job. This is not for you. Just right to your face. I'm not generalizing the whole culture, but
Yeah.
this is what
Yeah,
you
yeah.
can expect. But the thing is, you need to understand it's not them being rude to us. It's who they are. It's how they communicate, and they have a very direct way of saying things. So this is something you pick up, because again, you can't learn this uh, easily until you experience this firsthand. But what I'm saying is, when you get that experience, try to be more open-minded and see it as an opportunity, and learn about different cultures. So it's a very interesting thing.
And I think if anybody has any questions right now, you can either raise your hand and talk, or if you are more comfortable writing it on the chat, please feel free to do so. We can take a couple of questions right now if there's any. I see someone typing.
Okay, we'll talk about the resources that we can share, maybe.
Yeah. While we're waiting, we can, yes. So the resources, actually, I have not listed it down here yet, but what I can do is, for all of you who joined um, today, and even those who couldn't join and maybe kind of signed up, I will let them sort of I would either email some of the resources and maybe some key takeaways from this particular webinar. And if you're interested in a particular, like even websites that we can share with you, or some books that if you're interested in this particular area that might be useful for you.
Yeah,
Yeah.
definitely.
So I would just say just before, like, because I'm traveling with Teams. So in case I don't know how to draft your emails to send you this after, I would, let me just go to the, contact us this. Yeah, so you can contact me through any of these forms, call me, or you can email me at info@hybrid.ed.com, or you can find me on Facebook, Hybrid Education, or the Instagram at hybrid.ed. You can take a screenshot, or just you can message me in any of these forms, and I will definitely get back to you with the resources.
Yeah, speaking of resources, so I was planning to share some technical manuals and things that these aren't very sorry, highly technical documents, but these are FAA documents. I have a set of them. The FAA stands for Federal Aviation Authority. So these are sort of guidelines for structural design, electrical design, and maintenance practices, aerodynamic design. So these are sort of easy reads. They don't go for more than 20-30 pages. So maybe a bit more, but
I think there's one more question of like, so if you have the idea of starting to do this, it's better to do here or UK?
Well, I started in Sri Lanka. Me and you, Arjun, both.
Yeah.
We did the NT-UK program. I don't know whether it exists anymore, and then moved to UK. So,
I think
yeah,
currently, if you're planning to study like do the degree for aerospace aeronautical, I think anyway for you to complete it, you'll definitely most likely have to anyway transfer or
yeah,
do abroad that currently. That's what we have in hand. But in terms of working, there is opportunities, I think, in Europe, or well as a few, if you are aware, there is a few companies as well in Sri Lanka as well. But just in terms of starting, I think most of if you're looking at aeronautical engineering or aerospace engineering particularly, unless you look at maintenance, I think currently anyway, you cannot necessarily complete the whole 4 years exactly in Sri Lanka from what I am aware of. But you can start doing your first 2 years in one of the institutes here and then do the last two, or if you have 1 year left in the last year to do somewhere else, maybe that might be a possibility. That is in terms of studying wise. I think because we have like a time limitation a little bit, I will just quickly go through the upcoming webinars that we are hoping to do from Hybrid. Just to touch base, I'm not like, so we are looking at one on robotics and automation, calibration engineering, effective presentation skills, and an info session with Manipal University, the Dubai branch, with a business school. Those are a few that are coming up, and I would sort of give the dates, exact dates, probably maybe, and the next one might be end of April. So, but if you can follow us on any of those formats of Instagram, Facebook, or just email me or contact me with that phone number, I would make sure to give you a shout when we are doing the next webinar as well. Just because of the time constraint, unless, yeah, Damitha, if you have any final things to share.
no, I think we can move on.
Thank you so much. I think you shared so much today, which is extremely invaluable. And I'm grateful for everybody who could join today. And for those who couldn't, and if you want to share this, hopefully this is recording, so I can actually download and send you guys the replay, because I think there was a bit of a technical error today with the joining to the webinar with the link. I got some messages, so I did resend as much as I possibly can, but we can definitely still share. So I'm still trying out with Teams, but the next time I think I'm going to send to this one, I think I just send the link, but the next time I'll send the registration link, so I think you'll anyway get the actual the confirmation emails, and then it'll go into your calendar and reminders, etc., etc. But thank you so much. I see a lot of congratulations. It was a great initiative. Congratulations. Oh, so I'm glad everyone who was here. I think everybody who actually stayed this whole time as well. Like, yeah, so I hope this was helpful and you got maybe an insight that you normally wouldn't get. And Damitha, thank you so much for your time.
Not
And
a
I'm so
problem.
glad you did this with me because I've always said you explain things extremely well.
I
Like the one
tried.
person I do, like literally, because I can be a bit blunt sometimes with common sense. So, oh, Kavinu, thank you very much. This actually answered quite a few questions I had about the field. Oh, thank you so much, everyone. I would definitely try to share this because I think this actually went better than I should have expected. Because I think we shared a lot more and than I actually expected to. And like I said, it's a broad subject. And even if you were to go to aircraft maintenance or aviation regulatory stuff, you're going to be here talking for like 2 hours on one topic. So, like, if you guys are interested, do let me know if there's any other topics you would like to. I'll definitely try to arrange as much as I can. Like I said at the start, I'm driven by the fact that if there is a demand, I'm happy to see what we can do. So, but thank you so much, everyone, for joining. And Damitha, I love you. Thank you for
Well,
this. Yeah. But yes, thank you so much. And we'll have to end this here now. But hope you guys follow us on Instagram or Facebook or wherever that I can post. I'll just go back to that particular page just to take like maybe a screenshot if you want to. And I will try to send you all like an email again anyway with all these details. But yeah, thank you so much. Have a good evening.
guys,
Bye.
bye.
There's someone else wants to. Okay, thank you. Very interesting. Congratulations on the best wishes. Okay, now I saw someone writing.
Who's right?
My mother. Very interesting. Congratulations and best wishes. All right, thank you guys. See you all. Bye.